Okay, so look at more rigorously how the first order logic is defined. Well, let's start with signature. In propositional logic, the signature was very simple. It was just a set of symbols called atoms, which denotes either true or false about the facts in the domain. While in first order logic, there are two kinds of constants in the signature: function constants and predicate constants. And each of these constants is associated with some non-negative integers called error t, which denotes how many arguments that each constant can have. Okay. Now, this is non-negative, so that if the numbers start from 0. So there are special cases where function constants have no error t, no argument. So the error t0 function constants are called object constants. Likewise, predicate constants of error t0 are called propositional constants. Okay. So function constant denotes how you can talk about objects in the domain. Okay, so you can say A is an object constant, no argument. You can also talk about father of A. So in that case, father is a function constant that has only one argument. Okay, or you can have arithmetic function which takes two numbers as argument. Okay, and each of these actually denotes individuals in the domain. While in predicate constants, the um, predicate constants have predicate constants talk about some fact that holds true or false between the relation between the objects. So, for instance, where actually should be 1. So even can have only one argument, which means that some number that is given as an argument is an even number or not. Or greater than is a relation between the two numbers where the first number is greater than the second one. By the way, I talk about this meaning for now, like what is greater in things like even or plus. But note here that we haven't defined the semantics yet. So this is just an intuitive idea about the symbols. But for strictly speaking, for now, until now, it's just a symbols, which has no meanings yet. Now, in addition to these symbols, in first order logic, you can use something very similar to object constant, but these are called object variables, and you can use infinitely many variables even without specifying what is a signature. Okay, so the difference is in the signature is actually once you fix the signature, okay, you can use just that set of symbols, while the variables are not restricted to that purpose. Okay. Okay. Now using this, we can define what is a term, and term is from the signature. So in order to define a term, you should first fix what signature that you're talking about. And a term is actually defined recursively. Every object constant or every object variable is a term. So if I say like John, okay, is a name, okay, of some supposed to be some name of the individual, this is a term. And object variables, we usually use x, y, z, or sometimes with subscript. These are object variables, okay, and as I said, you can use these variables at any time, and these are terms as well. And there's a recursion here that for every function constants of error tn, f of t1 through tn are terms if each of these t1 through tn are terms as well. Okay, so there's a recursion here. So for instance, so father of John is a term of some signature where John is an object constant and father is applied to John. Or you can say that a and x, where object variable constant and object variable with their plus applied to that is also a term, because plus is a function that takes two arguments. Of course, you can write as a infix notation that is more familiar, like a plus x. One is of this important thing is it is a recursive, so the terms can be nested. So father of John, okay, was a term. Then this term can be applied to this as a term of this father. So father of John is a term, and this is a term. So father of this thing is also a term. Same way, x plus John is a term, okay, and a plus x plus John is a term. Of course, it may not make sense. How do you make a plus of John, add something to John? But again, that's something that we are concerning now, because we are just defining the syntax. Okay, the semantics will actually distinguish whether this is whether this is meaningful or not. Okay, so so this was just a term which was not present in propositional logic. Okay, so term is a kind of building blocks to talk about individuals. But we haven't talked about how to say what is a formula. And again, similar to term, we are going to define what is called an atomic formula. They look similar. So um, in atomic formulas can be either propositional constants that are predicate constants of validity 0, or similar to the function case, it is defined recursively, where R of T1 through Tn. Now note here that T1 through Tn are terms, and that looks very similar to the function, but note here that R should be a predicate constant. Okay, in contrast, here when we define term, that this f was a function constant. So okay, so they look similar, but the signature distinguishes what is a function constant and what is a predicate constant. Now, something that are kind of built-in predicate, this looks like a built-in predicate, is equality. So equality is actually not a part of the signature, but you can use freely. Okay, and you can talk about something is equal to another. Some terms are equal to another. The basic idea of atomic formula is kind of extension to atom in propositional logic. So in propositional logic, the atom can be true or false. So atomic formulas here can be true or false. Note here that propositional constants are very much like atom in propositional logic. So train late that you saw in the train example before is a propositional constant, and so it's also an atomic formula. But you can also say even of 2 or 3 is greater than 2. We can write this either way. Okay, this is an example of the second case. Okay. Well, and also you can use equality. Father of John is equal to John. Again, this may not be true, but don't care for now because we are defining syntax. Okay. All right. So having defined all these things, like term and atomic formula in a recursive way, okay, it's quite richer than propositional logic. Now we can define the syntax of first order formulas. Now this definition, if you see, compare with propositional logic, is very similar. Okay, so every atomic formula that we defined in the previous slide is a formula. Okay, and the zero place connectives like bottom and top are formulas. And so of course, in the case of negation and also the conjunction, disjunction, implication, equivalence, where this symbol, okay, denote the binary connective. Okay, so if F and G are formulas, their conjunction, disjunction, or whatever binary connective applied to F and G are formulas. So far this is very similar, okay, except that, instead of atom in propositional logic, you refer to atomic formula. Now here is actually a new part. Um, because atomic formula may contain variables, you can also write something like this expression, which is which use quantifiers. So this is called for all x, and this is there exists x. So if f is a formula, these two expressions are also formulas. Okay, so here's a simple example. We know a is a term, okay, and p, let's say p is a pretty constant. Well, p of a is an atomic formula, okay, and the its negation is also an atomic formula. So this is atomic formula here, and we can check that this second disjunctive term is also a formula, so that their disjunction is atomic formula. Their disjunction is a formula. Sorry. Why this is a formula? Well, it has this form, it is xf. So for checking that this is a formula, we need to check whether px and qx comma y is a formula. And of course it's a formula because it's a conjunction over these two subformula going to through the third case, okay? And you can see that p of x and qx comma y are both atomic formulas, so they are also formulas. So we can check that this is a valid string for the formulas applying this recursive definition. Now something to talk about here is, while we can define formula in this way, there are some meaningful formulas and not so meaningful formulas. So we are going to say some formulas we can assign the meaning, some formulas we cannot. And in order to do that, this definition is actually essential. So bound and free variables. So there are many variables that we can use, but they given a formula and given an occurrence in a formula, okay, we can say that whether this occurrence of a formula, or occurrence of a variable, is bound in the formula or not. Okay, so bound simply means that it is in the scope of some quantifiers with the same variable used in the quantifier. Okay, so the definition says that V is bound if it belongs to a subformula. Okay, so that is nested inside F, which has the form of QVG. Here Q is any quantifier for all or they exist. If you cannot find such quantifier scope, then the occurrence is free. Okay, so let's look at this example. So exists x, pxy, and not exists x, px, comma x. Note here that there are 1, 2, 3, 4, 5 occurrences of x, okay, and 1 occurrence of y. So if you look at this, so first, this x occurrence of x is actually bound because this already is in the scope of this quantifier. Okay. Similarly, the scope of this x is here. Okay, so this second x, the second occurrence of x, is also bound. On the other hand, this y that you see is not bound because there is no quantifier that contains exists y. Okay. Now, what about this? This x is bound, not because of this quantifier in the first, but because of this quantifier in the second. Similarly, this x, the two last x, is bound. Okay,